Hi, so the problem we're going to go over today is array index and element equality. In the problem statement is given a sorted array ARR of distinct integers, write a function index equals value search that returns the lowest index I for which the value in the array equals the index itself. And if there's no such index, we're going to return -1. So let's walk through some examples and see what this looks like. So the happy case we have here is -8. We've got 0, got 2, and we've got 5. And if we write up here the indexes themselves, you can kind of see just off a glance that 2 is going to be what we are going to return. And this is because the value at index 2 is equal to the index itself. So in this case, we are going to return 2. And then you have the -1 case. So let's see what an example of that looks like. So you've got -1, you've got 0, you've got 3, and you've got 6. And if we write out the indices themselves at the top, you can see that this will return us -1. And that's because there is no value in this array that equals the index themselves. So this is going to be -1. You can kind of imagine that if this was an array of all negatives, you would also return -1. So there are actually two kind of solutions to this problem. Let's look at the simplest solution you can kind of come up with. So if we go through -8, 0, 2, and 5, you can see that one of the things you can do is just a simple linear scan. So you can start at -8, and say, does the value here equal 0? It does not, so you move on. Now you're at index 1. And does the value at index 1 equal 1? It does not. See, 0 and 1. Then you move on, and you look at this one, and you can see that the value also equals the index itself. So in that case, you're going to return 2 right away. If you get through the entirety of the array and you never find a value, similar to what we have in example 2, then you're going to return a -1. So what does this look like in code? Let's take a look. Let me erase all this for us. So here is solution 1. So if we take a look at this, we will have, it's a simple for loop. It's going to loop through the array, and then it's going to do our check. Does the value at that index equal the index itself? Otherwise, we're going to return the index I. And if we go through the entire thing, we're going to return -1. So from a space-time complexity perspective, so what is the worst case time that we can expect from this? So in the worst case, we have to go through every element in the array. So in this case, the worst case time complexity is going to be O of n. And if we look at space, in the worst case, we're not allocating any new space. We are not creating a new input based a new array based on the input or anything of that nature. So from a worst case space complexity perspective, we're just getting O of 1. Now this can work. There's nothing wrong with this solution. It does get you what you want. However, it doesn't take advantage of the fact that the array itself is sorted. Typically, whenever you see a sorted array, you want to use binary search. And this is actually very applicable here. So let's see what binary search will kind of get us. Go ahead and erase all this. Okay, so when we're talking about binary search, how would that look? So if we go back to our example that we had, so we have -8, we have a 0, we have a 2, and we have a 5. So in typical binary search, what you do is you set up the you set your left. Oops, you set your left and your right pointer, and then you calculate some sort of middle. So let's just say our middle is here, and you would say, hey, does the middle value equal the value that you're looking for? Or in this case, really, you could kind of shortcut it and say, does your left value equal the index itself, or the right value, or does the middle value? It doesn't really matter. That's just a slight optimization that you can do. But here we look at it and we say 0. Does that equal 1? No, it does not. So in this case, if we take a look at the indices themselves, you can kind of know that if you look at 0 and you look at 1, you know that you either have to update your left pointer or your right pointer. So how do you know that? Well, if you look at the value here, you can tell that it is much less than the index value we have, right? So this is 0, this is 1. So you know that on the right-hand side is where your answer is going to lay. And that's true because you can see 2 is on the right-hand side. So in this setup, that's what you're kind of looking for. If the value at middle was greater than the value at the or the index itself, then you're going to update your right pointer. So in this case, we're going to say in the second iteration that this becomes the left pointer, and then the right pointer is here. So now you're going to calculate a middle value, and your middle value ends up being this guy. And now you're going to check again, do these two equal? Yes, they do. So you can return the value right away. So what does this look like as far as code goes? Let's take a look. Okay, so here we have the code that we talked about previously. You can see that I'm setting up the left pointer, and I'm setting up the right pointer, and then we're going until they are equal to each other, and we're calculating the middle index, so left plus right over 2, and you're checking if the value at the middle is equal to the middle index, and you're going to return mid. And this is the check. These two are the pivotal checks that you kind of do to say which way do I update the left or right pointers. If I look at this one, it says this is the case that we had here. So if we look at -8, 0, 2, and 5. So in the first one is right here, and this is mid. So this is going to say, does the value 0, is it less than mid, which is true, right? So this is 0, 1, 2, and 3. 0 is less than 1, so it's going to update left to mid plus 1, which will put us over here in the next iteration, and then the right one will be over here. You're just going to skip over it, and it's going to retain its current value. And then you're going to calculate middle again, so mid then ends up being here, and you can do the same calculation. If the value at mid equals mid, then you return mid itself. Yeah, and then let's say you had the negative case here. So the other case that you had was -1, 0, 3, and 6. So in this case, you set up your left and your right pointer. And let's set up these guys real quick. So your middle is over here, and you can see that the middle value is less than the index at mid. So 0 is less than 1. So you're going to update left, and you're going to put right over here, and then you're going to calculate mid again, and you look at this guy, and you say, are they equal? No, they're not. In which case, you're going to check, does the value at mid, is it less than mid itself? No, in this case, 3 is greater than mid, so you're going to update the right pointer. And in this case, your left pointer stays here, your right pointer goes here, and now they're equal. And so what you're going to do here is you're kind of just going to break out. You're done with it, and so this will return you -1. So what is the space-time complexity of this solution? So let's go ahead and write that out. So typically when you're dealing with a problem like this, binary search kind of has its own, it's going to be O of log n. This is just binary search itself. You're kind of, this is just a property of binary search itself, I suppose. And then space-wise, it's the same. You're not allocating any new space, so it's just going to be O of 1. Yeah, so there's not much more to say about this problem. It's just an application of binary search. And I would say if you're looking for a pattern, whenever you have a sorted array, that should kind of guide you towards the idea that you want to use binary search. And it's more performant. So, thank you for watching.